In this video, we're going to extend our model for the spring mass system by adding friction to it. So previously we had a mass which was sitting on a flat surface with no friction, and we had a wall and we had a spring connecting the two. So this kind of system here, and we were imagining that we were stretching the spring out a little bit, defining that displacement as our x position, and then recognizing that we'd see oscillations once we let it go. You probably weren't too surprised to see a sine and cosine coming out of the solution to that system, because sines and cosines seem a natural fit for something that's oscillating back and forth over time. We're going to see that friction changes that up a little bit though. So imagine we have this scenario and we look at the free body diagram for our block, which is usually more rectangular than that, but we'll work with it. So the first thing that we had was our spring force. Sorry, the first thing we always have is our gravity force, but we're not too interested in that because it is perfectly balanced by the normal force provided by the ground. In the horizontal direction is where all the interesting things are happening. With our spring force, and imagine we're moving in this direction, we would have a resistive force, which would be F friction. So we're going to be interested in those two forces, friction and the spring. How are those going to help us understand the scenario? Well, of course, the sum of the forces defines the mass times acceleration. And so we can write those down individually, where we have the F spring plus the F of friction equals mass times acceleration. The spring force we've already seen, negative kx. Whatever the displacement of the spring is away from the equilibrium point, we're going to scale that by the spring constant, make it negative to push us back, and that'll be the magnitude of the spring force. The mass times acceleration we saw earlier, and that was just recognizing that acceleration of what? Well, of this block. That means that we're talking about the second derivative of position for that. The friction force is new, and without going into the master's level thesis of friction, because anyone who goes into mechanical here, there are tons of models for friction, but for our purposes, we'll keep it relatively simple. A very good approximation for this kind of scale is to talk about friction that is proportional to the velocity. So proportional to the velocity. So if you're moving at 1 meter per second, you have a certain friction. If you double the speed, then you double the friction that goes with that. Now, the only extra ingredient we need with this is a negative sign. Why do we need a negative sign? Well, if you think of the direction the force acts in, if we're moving to the right, the friction is going to pull us to the left. So if the velocity is positive, we're going to need a negative component to talk about the force resisting that motion. And likewise, if the block is moving left, then the force of friction is going to be slowing it down, so it's going to be pulling to the right, or the opposite direction again. So again, this negative sign here captures the left or right motion of the block. Okay, now this is a more complicated differential equation. We have our x's, but now we have a velocity term in there, and sines and cosines are probably not going to cut it completely anymore. In fact, we can see that just from our intuition. If we move all the terms to the other side, they become positive, so you get a positive c and a positive kx, just going back here, taking these terms and bringing them over to the right-hand side. This is just a convenient way to make our equation equal 0 to give us some kind of consistency of what goes where. And in the no friction case, we had pure cos of square root of k over m t's and sine of square root of k over m t's. That's what we would get if there was no friction, because if there's zero friction, this term doesn't even appear in our equation, and we're back to exactly the same scenario we had before. However, if we do have a small c, then we expect to see this. We expect to see, say we stretch out the spring, and then we let it go. It's going to oscillate, but the oscillations are going to die down over time. So still oscillations, but with decreasing amplitude. Okay, and just think even further, imagine like one of those doors with an overly damped spring in it. So these are like industrial doors going into stores. If you let them go, they just kind of creep towards closing or equilibrium. Maybe they kind of bounce-ish once, but then they're really, really sluggish. That's where you have a high friction scenario happening. Yet all three of these scenarios are described by exactly the same equation, just with different values for c. And pretty clearly cosine sine are not going to work for this model at all, because this does not oscillate, it just kind of creeps down. How are we going to try to find a solution to this general equation that's still going to cover what we know about the no friction case, but also cover these two new cases? Well, the answer is going to lie in a little diversion, and that's going to be looking at introducing a secret sauce, which is the square root of -1, or the number frequently called I, the imaginary number I. We're going to be able to combine that with a simple exponential and see how that plays out as a way to solve this kind of equation, and it's going to turn out to be incredibly powerful for solving a whole bunch of equations around this type. What happens when we try to introduce just the idea of the square root of -1, and specifically if we pair it with the exponential function, the natural base e exponential function? To make our lives a little bit easier, we're going to go back to the c = 0 no friction case for our spring mass system. And to make it simpler still, we're going to treat the spring constant as 1 Newton per meter and the mass as being 1 kilogram. So bare bones, this is the equation where we have our acceleration, mass times acceleration equals -kx. What does Newton's law tell us about the motion of this system? Well, let's just confirm and remind ourselves how sine of t can be shown to satisfy that equation. If we want to show a solution satisfies the equation, we have to plug it into both sides and show that both sides are equal, left and right hand side. For the left hand side for this though, we need x double prime. We don't have that. We have to get there eventually by taking derivatives as we go. So if we take the derivative of sine, we'll get cos, and x double prime equals negative sine of t. Okay, so that's what our left-hand side is. So our left-hand side is equal to x double prime, which is negative sine of t. Meanwhile, our right-hand side is equal to negative x, but we just said x was sine of t, so negative sine of t. So these things are equal, and if that's the case, we have something that satisfies the differential equation. Let's explore e to the it though, and what we're going to do is just treat I as a constant. It's just some number. It happens to be not a real number, but let's see what happens. If our x of t equals this, we're going to try to show that this satisfies this differential equation, and all we know about I is that it's equal to the square root of -1, or that, written another way, we square both sides, we get I squared equals -1, saying exactly the same thing. Well, we still need, if we're going to check that this value or this function satisfies this equation, we're going to need x double prime. Well, x prime is equal to, sorry, I'll make the double prime there a little clearer. x1 prime is the derivative of this. We know the derivative of exponentials are the same exponential again, times the constant, or times the derivative rather, the derivative of the exponent, and here that's just a constant I. We were making some assumptions, I'm not going to lie, but they turn out to be totally valid assumptions if we're willing to accept that I is a perfectly valid constant. And if we take it one more step, we get the derivative of this is some constant times e to the whatever, so we get that times another I e to the it. Well, that is equal to I squared e to the it. Oh, well, what's I special? I isn't just some random constant. It's the constant that when I square it gives me -1. So this is negative e to the it. That means our left-hand side of our equation, again, probably should have put a nice number here, so we know we're talking about the same equation for both, even playing field. The left-hand side is x double prime, which is equal to negative e to the it, and that should set you up nicely for the right-hand side logic, which is negative x. As long as we can plug the x in and get this equal to negative x, well, sure enough, it's negative times, we said x was e to the it, e to the it. And these two are, just like sine worked, these are equal. Exclamation marks. So sine satisfies this equation, and e to the it also satisfies it if we're willing to trust that I can be treated like a constant. This is news. This is a gateway to one of the most famous equations in mathematics, Euler's equation, or Euler's formula. We better spend some time looking at this I thing and just kind of seeing how complex numbers work before we go too far down the road here, but we are on to something major here.